Oh, we get our. This is like a lot.
Yeah, I have one plus. I guess it's like, and you guys like there's other times, but I guess it's like if you get level selection. Space on your.
Yeah, we got a junior.
I did. Is that me?
It's all they all.
Oh, yeah.
Well, so it's like that 70 to like.
You really half the material.
But it's fine, I got an 84 in the class. That's not that bad.
That's like 3, this is 5.
It's like, I think
About, I think around. I don't know.
Okay, if we can turn to page 15 in your FRQ packet 5. We're going to work through page 15 and 18. So I want to focus on a rate in, rate out problem. So it's a very high chance that you're going to see a rate in, rate out problem on your AP exam 2 Mondays from now. So let's look at number 1 here. This is number 1 from 2019. Fish enter a lake at a rate modeled by, this is calculator. So number 1 and 2 will be calculated. Fish enter a lake at a rate modeled by function E, given by E of t. Fish leave the lake at a rate modeled by a different function, function L, L of t. Both E and L are measured in fish per hour, and t is measured in hours since midnight when t is equal to 0. So part A, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. So part A is pretty straightforward. We're trying to get from fish per hour up to the number of fish. So an integral can help us get there, right? So thank you. We can just do a definite integral and then math 9, make the calculator do our steps for us there. Part B, what is the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m.? So now we're working with L of t. We only care about the number of fish that leave the lake, so we're not going to involve E of t for part B. But the difference is here is that they're asking for the average number, the average rate, basically, right? So average rate. So that average to kind of clue us in that we're looking involving average value theorem to help us get to our average rate. So 1 over b minus a. Integral of L of t. And then we do math 9 again, make the calculator do all the calculus steps for us there. Yeah.
The boxes on the side.
Oh, I made this key when they released the test a few days after the exam. So I was just predicting what the points were going to be like. I don't think this ends up being the actual points, but just kind of talk a little bit about points. Every FRQ is going to be worth 9 points. So they're going to, but you're not going to know how they're going to subdivide the points. But every part is going to be somewhere between 1 and 3 points usually. Sometimes there's a 4-point one, but usually between 1 and 3 points. All we know is that they're going to add up to 9 points. Yeah. So if you can earn between 4 and 6 points per FRQ, you're getting you're in a good spot. You're in range to get a 4 or higher. So yeah. But every FRQ is going to be worth 9 points. And typically, the first part is less points, and then the part C and D are usually worth more, but it doesn't have to follow that pattern. Okay, so I think parts A and B are pretty straightforward. There's just kind of one-step process to get to our answer. Any questions with A or B? Okay. Part C is kind of like the bulk of this problem here. So let's look at part C. Part C says, at what time is the greatest number of fish in the lake? So we see that word there, greatest number. That should clue us in that we're trying to do something with extreme, or they're trying to get us to use extreme value theorem because of that word greatest. We're looking for greatest value, least number. The understood word is absolute. It's involving asking you about absolute max and absolute min. So, but before we can find out the greatest number of fish, we first have to figure out what formula we're going to use to actually find the number of fish at just any moment in time. So because this is a rate in, rate out problem, we have this rate in, rate out formula that we want to be able to know how to use. So this rate in, rate out formula basically is involving all these moving parts and putting it all together. So the formula looks like this. Okay. Total amount is equal to the initial amount plus the amount added minus the amount removed. So if you know you're going to involve this formula, if they tell you like a formula for rate that something is being added, and they tell you another formula for the rate at which something is being removed. And so we want to be able to recognize that and to be able to use that formula. So for us, we're going to be using this one here. So I'm going to use f of t to represent the number of fish in the lake at any moment in time. So f of t is equal to f of 0. And we're not always going to say f of 0, but the reason why we say f of 0 here is because that's what they give us, right? They give us that data. So that's going to be our given or our initial amount. And then the amount added is going to be, if we accumulate the rate at which fish enters into the lake between 0 and some time period, we're going to be able to get the total number of fish that's entered the lake in that time period. And then if I take the integral of L of x, that's going to accumulate the number of fish that's left the lake, and I can find that number. And if I put all those three things together, we can figure out the number of fish at any moment in time. Okay, so that's the formula we're working with, but we know that if we want to do extreme value theorem, we have to find critical points and endpoints, right? And critical points comes from the derivative, so we have to build our derivative f prime and then set equal to 0. So f prime is equal to, we know f of 0 that's just a constant, so that goes to 0. And then we want to find the derivative of this, which second theorem will just get us down to e of x level. And then we also want to find the derivative of that last term, but we know second theorem will also bring that level down as well. But now f prime is just a nice clean e of t, right? We know that the derivative of integral will wipe each other out. We just plug the upper bound in for the x. So e of t minus L of t, a nice clean f prime. And now to find the critical point, just set f prime equal to what? 0. So this is a calculator question. So what you can expect is they're going to ask you to find that critical point using your calculator. So the strategy here is you want to graph this and then look for the x-intercept. Okay. All right, let's practice doing that. So I'm going to have y1 hold E of t. I'll have y2 hold L of t. And then for y3, I'll just say y1 minus y2. So I'm going to make sure that I'm unhighlighting my y1 and y2. That way I'm only seeing my graph that I want to see. I'm just looking for the x-intercept there. So if I do zoom 6, that may not be, oh, that's not bad. All right. So again, if your graph is showing really vertical lines, then you probably want to go to your window and just adjust your y-min, y-max. In fact, I'm still going to do that. Just I see that the graph on the right is still a little sharp in terms of its slope. So what I'm just going to say from -30 to 30, but you're just, you're just playing with numbers to get something where a graph that is easier to read. That's a little better, easier for me to trace if I don't have a line that looks like a vertical line. So I'm going to do, I know I'm looking for a value between 0 and 8 because that's my domain when t is between 0 and 8. So that's the x-intercept I'm looking for. So second trace, 0. I'm picking a point to the left of the x-intercept first. And then picking a point to the right of the x-intercept, hit enter. 6.203. So we know we want to find the number of fish at 6.2. We want to find number of fish at 0, and we want to find number of fish at 8. So that's testing, going through our extreme value theorem, testing our critical points and endpoints, and we're inserting them all back into our f of t equation. This is the equation that's going to tell us the number of fish at those moments in time. Oops, L of t. And then we're making the calculator Math 9 do all the calculations for us. They're asking for the time where the most number of fish is going to be in the lake. So even though 135 is going to be the most number of fish, they're asking for time. So we're going to provide t equals 6.203. And you don't have to provide any justification in terms of, listing conditions for extreme value theorem. What they want to see is that you're testing the appropriate endpoints and critical points, and that you're putting it into the appropriate function, and then you're making your conclusion based off of your data. Part D, is the rate of change increasing or decreasing? So we know rate of change is at fish per hour, but it's asking, is that rate of change increasing, decreasing? That should clue us in that they're asking about a derivative below my EFT and LFT. So, well, we have a formula for the rate of change, right? We have F prime. So we know for part D, our starting formula is F prime is equal to EFT minus LT, right? We have this as our starting point. We have something that tells us the rate at which fish is either increasing or decreasing in the lake, right? These are all in terms of fish per hour. But it wants to know, is the rate increasing or decreasing? So we know we're going to be involving the second derivative. So we're going to build our second derivative. And this should be pretty straightforward. These are both in function notation. We just take a derivative down for each of them. And it just wants to know, is the rate of change increasing or decreasing at t equals 5? So we just want to know, is f double prime going to produce a positive or a negative value? If f double prime is positive, we know the rate is increasing. If f double prime is negative, then we know rate is decreasing. So we do math 8 on E of t and L of t and make the calculator find that value for us. All right, next up, page 18. Now, you may not see a related rates, full related rates FRQ on your AP FRQ exam, but I would say that chances are high that you're going to see some related rates problem. So, be ready to know, when to apply related rates. So we know related rates is going to be involved if there's time involved, or if they're asking about the rate of change with respect to time. Those are all good indications that we're going to have to build our derivative and get a bunch of d over dt's to show up as we do that. So this is page 18. We have a cylindrical barrel with a diameter of 2 feet, contains collected rainwater. The rate of change of the height is followed by dh dt, where h is measured in feet and t is measured in seconds. Find the rate of change of the volume of water with respect to time. So there's the hint there, with respect to time. We know time is going to flow through our equation. We know d over dt. We're going to make those pop up in our derivative when the height is 4 feet. So indicate the units of measure. So we have our volume formula. They will provide that for us. Find the rate of change of the volume. So let's look at volume first. Volume is pi r squared h. So if we think about a cylindrical container and the water level is decreasing or increasing, doesn't really matter. And if we think about, okay, the water level is going to be changing, right? The height is going to be changing. But what about the radius of the water level? Is that ever going to change? It's always going to stay the same. So what we do know is that there's no need to hold on to our R variable. We only want to hold on to it if we realize that there's if it's a moving part. We do need to hold on to our H variable, even though they tell us our H value. We don't want to replace that, at least not before the derivative. So sometimes you're going to get a bunch of values for variables that are not going to be suitable until after the derivative. But in this case, we can replace the R in for 1 in for R because it's never going to change. If it's never going to change, there's no need to hold on to that variable. So I'm just going to go ahead and plug that, replace that R with 1. And that will allow us to have a starting equation that's a lot easier for us to find the derivative. So remember, time is going to impact every variable here. So let's now find the derivative. Okay, V becomes what? dV over dt. Pi h, it's like a 3x, right? So what's pi h's derivative? This pi, we know the h goes to 1, but we're asking for h's derivative with respect to time. So we need to attach a what? dH over dt. So I think that's the hard part that I think a lot of students experience here is I saw on the multiple choice test where you're trying to find the derivative, but then you forget to include the d over dt's, and then you didn't have a way to plug in and find your missing value. So make sure that when you go through, if you're doing related rates, a lot of times the derivative is easy. It's just power rule. So just apply power rule and then just make sure you include your d over dt's as you build out your derivative. Okay, so then once we have that, we can just go ahead and make all of our values get plugged in. Sorry, I'm running out of time here. So, but I can go back and review some of this problem again tomorrow. But if you guys can make some progress tonight, page 15 through 20 for the 2019 FRQs, and tomorrow I'll finish this problem and I'll take out the problem from either 2018 or 2017. All right, come get your phones. Thank you.